All right. Hello. In this video, we're going to be looking at the physics journal, which is about work. So the guiding question here is how do you increase or decrease an object's energy? And we got two big ideas here, so that's a little different. But big idea number one is that energy is transferred from one object to another by the process of doing work. And so that like an equation form of that statement would be that work is equal to the change in energy. Remember that triangle there is a delta, and it means change in energy. So that's basically final energy minus initial energy. The amount of work done is the same as the amount of energy gained or lost. So work is just basically what we call the energy that's added or subtracted. So like basically you want to increase something's gravitational energy, you have to do work on the object, just meaning like you have to put energy in. And then we also call it work when energy leaves the system. So work would be negative if energy is transferred out of your system. So if maybe you lower an object down or you slow an object down, the work would be negative because energy is leaving, basically. All right, getting into big idea number two here is that work is now how do you change the energy in something? How do you do work? Work is done by when a force acts on an object through some displacement delta x, meaning that if you would like to add energy to something, you have to apply a force over a distance. So basically, you just have to push something for a certain distance. So that would be, in the situation that we have right here, let's say we got a little block here. We got a force F being applied to that. The amount of work done would depend on how big the force is, and then also how far you pull it. You pull it further, you do more work, you add more energy, and so that's kind of the idea there. So only the component of the force that is parallel to the displacement affects the object's energy. So in this example, so from above, force parallel, the little two lines right there mean force parallel, equals just the x component of the force, the horizontal component, so F cosine theta. And because we're looking for the part of the force, the one right here in red, that is parallel to the displacement that you apply. So thus, work is equal to force times by your displacement times by cosine of theta. So again, we're looking for just this part of the force that's parallel. So let's see here. So next up, theta is the angle between force and delta x. So in this case, right, where your force and your delta x are in the same direction, both to the right, then theta is equal to 0. Cosine of theta, you could type that in, is equal to 1. So basically you would end up with just F times by delta x, just the force times by the delta x. And that's going to add energy because, right, you're pulling in the same direction that you're going. Let's just say that the force is opposing. So maybe this is an object that's sliding to the right, but you're applying a force to the left. So these would be in opposite directions. So probably what this would indicate is that the object is slowing down. So mathematically what happens is that theta would be 180 degrees because, right, those are separated by 180 degrees. Cosine of 180 is going to give you -1. You could try that, plug it in your calculator, see what you get. You're going to get -1. That's going to tell you that work is negative, which means that energy is leaving. Again, thinking about the situation that I just said, like you have an object that's maybe sliding to the right, but you're pushing in the opposite direction. That's going to slow that object down, subtracting energy, right? In this case, in the case that I was describing, subtracting kinetic energy, right? You'd be losing kinetic energy. Lastly, we have this force where maybe the force is straight up, but then the displacement is to the right. In that case, theta is 90 degrees. Cosine of 90 degrees is 0, so the work is 0. And that's because this force is not contributing to your delta x, right? This delta x is happening regardless of that force. So that force is not increasing or decreasing the energy. So maybe you have something that you're just kind of carrying along. So you're applying an upward force to lift it. And then you got your delta x there to so this basically this force is not helping change the energy. It's not increasing the kinetic energy by making it speed up. It's not increasing the gravitational energy. That force just is not contributing to that delta x, that change in distance there, because it's not in the same direction or the opposite direction. So let's take our first example right here. Let's see here. I got it right here. So example 1 says a 1.5 kilogram book starting at 4 meters per second slides to rest on a surface. There is a 5.5 Newton force of friction. Find the work done by friction. Okay, so thinking back to we have basically two equations, right? We could find it by the change in energy. Work is equal to your change in energy. You could also find it by your F times by delta X times by cosine theta if you knew forces in delta X's. So let's take a look at what we know about this one. We know the initial velocity. We would also know the final velocity is 0 because it's coming to rest, right? We know the force, but we don't know the displacement, right? So we can't use work is equal to force times by distance because we don't know the distance, right? Right, we can't use this one because you don't know delta x. So what that means is we're going to have to use this one to find the amount of work done. And we aren't going to be able to find that because remember that work is equal to change in energy. We know what the initial energy is, and we know the final energy is 0. So we know that work is equal to delta E. And we know that delta E is equal to final energy minus initial energy. So our final energy is 0 because we're not moving, and our initial energy is 1/2 mv squared. So 0 minus, right, 1/2, you know the mass, 1.5 kilograms. You know the velocity is 4 meters per second. So your work is going to be equal to negative 0.5 times by 1.5 times by 4 squared is equal to negative 12 joules. Okay, now the negative sign makes sense, right? Because you're decreasing your kinetic energy. So, right, you're slowing down. So it makes sense that this object is losing energy. So it makes sense that work is negative. So now it says find the distance the book slides. So in this case, we're going to use the other equation, cosine of theta. So let's see here. We know that our work is negative 12 joules. We know that our force is 5.5. And let's see here. If we think about this, let's just say that our object is going that way. So that's our delta x. Our force, right, that force of friction is going to be in the opposite direction of that. So I'm going to put a negative 5.5 there because the 5.5 is in the opposite direction as my displacement. And that's going to make my angle 180 degrees. So, which is going to give me negative 1. So I have negative 12 because I'm losing energy is equal to, so now I have, let's see here. Sorry. I'm gonna take that back about the negative sign here. I'm not gonna put that in because the 180 is taking care of that negative sign. So I apologize for that. You do not need to put the negative sign right here because the negative sign is going to come from the 180. So I'm taking care of the direction of my force using this theta right here. So I apologize. I was thinking about that wrong. So I'm gonna get so again, just you can put a positive 5.5 here. This is going to give you your negative 1, so I'm going to end up with 5.5 times by delta x times by negative 1. So negative 12 is equal to negative 5.5 delta x. Divide by 5.5. So divide by negative 5.5. And you're going to get that delta x is equal to, let's do this. Well, the negatives are going to go away, so you're just going to have 12 divided by 5.5, and that's going to give you 2.18 meters. And there you go. Moving along, we got the next problem here. In this case, this one's pulled at an angle. So we have, we got this box right here. It's a 5 kilogram box. It's pulled 2 meters across a frictionless surface. The force of 14 newtons is applied. So that means that's 14 newtons is applied at a 35-degree angle to the horizontal. How much work was done on the block? So we got to ask ourselves, which equation are we going to use? Do we know the change in energy, or do we know the force and the distance? In this case, we know the force and the distance, right? We know that the force is 14 newtons. We know that the distance is 2. And so we're going to use that work is equal to force times by your distance times by cosine of 35 degrees. So, right, we got our 14 newtons there. We got our the distance we pull it, which is 2. And we got cosine of 35 degrees. So work is equal to, let's see here, we got 14 times 2 times by the cosine 35 degrees. And that's going to give you 22.9 joules. 22.9 joules. So there we go. Next, assuming that the block was initially at rest, how fast is it going after being pulled for the 2 meters? Okay, so for this, we're going to use the other one. Work is equal to change in energy. Change in energy is equal to final energy minus initial energy, right? Any delta is final minus initial. So we're talking, of course, about kinetic energy here. So work is going to be equal to 1/2 mv squared because it's moving at the end and it was not moving at the beginning. So the initial energy was 0. So basically the work is equal to the amount of kinetic energy the object has, because all the energy that we put in is going to become kinetic energy. So we put 22.9 joules of energy in. We know that the object is a 5 kilogram block and we're looking for the velocity. So we got 22.9 is equal to 2.5 v squared. Divide by 2.5, so 22.9 is going to give you 9.16 equals v squared. Square root both sides. And you're going to get that v is equal to basically 3.03. But you could just have 3 basically. So there we go. All right, last one here. So an 8 kilogram package is carried at a constant speed of 4 meters per second to the left. How much work was done? Now, let's just think about this, right? So in this case, the forces that are acting on the object are, as you carry it, right? You have the weight of on the package. You have the normal force, or the lift force on the package. And then obviously it's going to be, it says it's being carried to the left. So it's being carried that direction. So that's your delta X. So first up, there's a couple different ways of thinking about this. So neither one of these forces are in the direction of delta X, right? So neither the lift force nor the force of gravity are assisting in moving this thing to the left. So, basically meaning that our work is equal to force times by distance times by cosine theta. Well, theta is 90 degrees, so the work would be 0 because cosine of theta is 0. The other way to think about it, right? So cosine, it doesn't really matter what force is or delta X is. This cosine right here is 90, or its cosine of 90 degrees is 0. So 0 times by whatever that is going to give you 0. Also, neither one of these forces are assisting in making this thing, are assisting in moving the object delta X. The other way to look at it is, right, work is also equal to change in energy. Well, we haven't actually changed our energy at all, right? Right, because we didn't change the kinetic energy because it goes at a constant speed. So we didn't increase or decrease that. We didn't change the gravitational energy because we didn't lift it up or move it, lift it up or lower it down. And we didn't change the elastic energy because there's no elastic energy in this situation. There's no spring. So the work is zero. And again, I've kind of explained two different ways in which we can think about it being zero. Again, neither one of these forces are assisting in moving the object to the left, right? Because they are vertical forces, so they're perpendicular to that, so they don't help or hurt us moving this object to the left. Mathematically, that's because these are perpendicular, so that means in 90 degrees. So this would be cosine of theta would be zero. Zero times by anything is zero. The other way to look at it is, right, we did not change the energy of anything. So therefore, we didn't increase or decrease the energy, didn't increase or decrease the kinetic energy, the gravitational energy, or the elastic energy. So therefore, the work would be zero. So, all right. Thank you for watching. I hope this helps. As always, if you have any questions, let me know. Thank you for watching.